So in this lecture we are gonna introduce the notion of the implicit function theorem, and we are gonna discuss. So I guess this is lecture 8. I don't exactly remember. Let me check once. Okay, so this is lecture 9, I guess. Yeah. And in this lecture we are going to introduce the notion of the implicit function theorem. Fine. Okay. So better to see the implicit function theorem is typically a bit confusing when you go through a book or go through a written note, because it often you get confused between the coordinates and the points and what it actually means to talk about an implicit function theorem. It sort of confuses you a lot, so it's better to dedicate this lecture in order to understand the motivation behind it, and sort of why we study the implicit function theorem and what it actually relates to. Okay, so in this lecture we will be so that's why I wrote introduce. So we are going to introduce the implicit function theorem, that is the notion of what it deals with technically, and in the next lecture we will give a formal proof of it. Okay. So what is an implicit function theorem? Okay. Now whenever we study functions, in one variable, or rather let me be a bit more strict. So let f be a map from R to R. Okay, right? Then by the definition of a function, what it does is that it chooses a value from R, from the domain, and it assigns a value y, which is also in R. Right? This is how a function behaves. Right? It takes values from the domain and assigns a value from the codomain to it. Right? That is exactly how a function works. Now we know that for a function to be well defined, there is something very technical, that two of the elements from the domain cannot have the same codomain element. Right? We know that. What does well defined means? What do we mean by a well defined function? So a well defined function means that whenever I choose x1 to be equal to x2, I must have f of x1 to be equals to f of x2. Right? This is what typically means, right, for a well defined function. That is, if I choose some value x, it cannot take in two different y's. Okay, that is, you cannot have a one to many function thing of that sort. Okay. Yeah, so that is one thing. And the other important notion which you have whenever you talk about functions is the notion of a graph. Okay. And what is a graph technically? So if I talk strictly geometrically, what you do is that you take in the Euclidean plane, the affine plane or the Euclidean plane, the usual R2 plane, and you start plotting the function by choosing the y's and the x, and these are the things you already know. So we get suppose something of this sort. Okay, something which looks like a curve. If you are acquainted with what a curve looks like, you get a thing of this sort. So this is what we call a graph of x, or a more technical definition for a graph should be, so it is the collection of all the points of the form x fx, such that x comes from R here. Fine. Fine. And this is quite easy to observe, because whenever you choose a point here x, you will get a corresponding point here, which is exactly the point f of x. So each of the coordinates on this structure is of the form x and its image under f. Right? This is what we call a graph. And given a geometrical structure like this, the obvious way and one of the most important ways to verify whether it's a graph, because technically for this geometric structure to be a graph means that there is some function f such that I can represent this structure using this set or this collection, right. And obviously functions should satisfy this property as well, and therefore the way we usually judge whether a given geometric structure is actually a graph or not is the vertical line test, and that is something you guys should know. That is, you choose a point, you choose any point on the domain and you draw a vertical line, a perpendicular vertical line, and you check the points of intersection of this line to the graph or to the geometric structure. If there is a single point of intersection, then you are good to go. That will give you a graph, because then the function, then you will know that this is actually the graph of some function, right, because of this well definedness of functions. Otherwise it won't be. We will come to see examples. So this is what we call a graph, and there is another which is kind of similar to a graph but not so similar. That is the notion of a curve, or more technically a level curve. Okay, yeah. So suppose I have a function g from R2 to R, right. What are the level curves? So we define that a level curve is the collection of points xy in R2 such that the image of this point is some constant c. Okay, this is some constant. So the level curve is basically the collection of all those points in the domain whose image is constant, whose image is strictly constant. Okay, that will technically give you a level curve. Fine. Let us quickly get an example. Let's say G is a map from R2 to R such that G of xy is equals to x plus y, and then what is the level curve? Level curve of gxy equals to 1, and you can easily observe then this will just give you a line, right, which passes through the coordinate 1 0 and the coordinate 0 1, right, the coordinate 1 0 and the coordinate 0 1, and this is what we call a level curve. This is what we call a level curve. Fine. Now given a function from R2 to R, you can draw a level curve with ease, but the question here immediately arises that this geometrical structure sort of seems to be extremely related to the notion of a graph, because you can immediately see that the graph is geometrically sort of similar looking like the level curve. But here arises the question, that is, given a level curve given a level curve, can you always get hold of a function whose graph is this level curve? So the question is basically, given a level curve, does there exist a function whose graph is this level curve, whose graph is this level curve? Okay. So let us first analyze this. Okay, let us first analyze this. See, given this to be the level curve, and we have just seen that this is basically the level curve of g of xy to be 1, where g of xy is given as x plus y. Now we can sort of immediately observe that if you choose the function f from R to R such that f of x is equals to 1 minus x, okay, or rather I am talking about the function y is equals to f of x equals to 1 minus x, then you can immediately see that this geometrically when interpreted actually resembles this line, and which is exactly this level curve, right. So therefore this level curve, which was sort of geometrically the thing, collection of all points xy in R2 such that g of xy is equals to 1, this is exactly equal to the graph x f of x, yeah, or rather, yeah, x f of x such that f is a function from R2 to R, f is a function from R to R, which is given by this, or rather I can simply write it as f 1 minus x, rather it should be, this will be better, such that f of x is equals to 1 minus x. Fine, clear? Okay. So in this case we see that this level curve, for this level curve we have a function whose graph is actually this level curve, but is it always true? Okay, the question is it always true? Okay, so is this always true? So what we have is that we have sort of got an answer to our question, that is, given a level curve, does there exist a function whose graph is this level curve, and a sort of an answer is that probably, right, because we have counted for an example where this actually happens. So probably it must be, it might be general, but obviously things in mathematics which look to be true in general are not generally true. Yeah, so consider the function, so yeah, so consider the function f from R2 to R such that f of xy is equals to x square plus y square, and consider the level curve f of xy equal to 1. Fine. Now again this is quite clear that this represents the unit circle in R2, right, this represents the unit circle in R2. Fine, let me adjust this a bit. Yeah, so fine. Yeah. So this represents this unit circle in R2. Now my question is that whether we will be able to get some function whose graph is this circle, and that is not possible. Why is it so? Because we have just seen that for a if you have a function whose graph is this this circle, then this graph must satisfy the vertical line test. Otherwise the function whose graph is this circle, the function itself won't be well defined, and we can easily see that the vertical line test is actually not satisfied in this case. Why is it so? See, if I choose any point here and I draw a vertical line, then it intersects it at 2 points, therefore the vertical line test is not satisfied. This is the first thing. The next thing to observe is that let us quickly go back to the way we represented the curve. See, this is not the only way to represent the graph. I could have also represented it in terms of f y y, such that y is in R R, right, where I would have represented x as 1 minus y. I could have done this as well, right. So so for a given graph I can represent it in either way. I can choose the dependent variable to be one of the coordinates, right. If it might be possible that if I can't represent it in terms of in terms of some variable, I might be able to represent it as a graph in terms of some other variable. Fine. But see that here in this case it cannot be represented in terms of a graph in terms of y as well, because here it also fails the vertical line test. In this case it will be a horizontal line test, things similar like that. Fine. Okay. Therefore this circle, so this has, or rather this admits no function whose graph is this level curve, is this level curve. Fine. Clear. But there is something very important to observe in this case. See, suppose I draw the circle once more. Okay. Why can't I rotate it? Okay, so remove it. Suppose I draw the function once more. Okay, I draw the circle. Fine. Let me decrease it a bit. Okay. Now observe that if I don't consider all of the circle, but I consider only the semicircle, let us say, if I consider only this part, okay, then you will see that it actually satisfies the vertical line test, because if you consider only this part, then choosing a point here x and you draw a vertical line here, you will see that it intersects it only at one point, a single point. So this semicircle can admit a graph in terms of some function, right. In fact, this is just, so if I consider the level curve once more, so it was given by x square plus y square equal to 1. So this just admits the positive square root, this just admits the positive square root. And similarly, I could have also considered this part, okay, this will admit the negative square root. Fine. Is it clear? Okay. Therefore, the question here immediately arises that the implicit function theorem, or rather we have not mentioned what the implicit function theorem is, so rather let me not talk about that at this point, but it actually gives us the fact that given a level curve, it is not that fruitful to talk about existence of some function whose graph is that level curve globally, right, but we might talk about it locally. We might talk about some part of the level curve which might admit a function whose graph is that part of the level curve, right. And we have often seen this in mathematics, that it is not always fruitful to talk about things globally but locally, right, and local properties serve a lot of purpose. Fine. If you have studied an analysis, or if you have studied topology, you will see that the major purposes are satisfied by local things, okay. We talk about local bases, we talk about local compactness, we talk about local convexities, and so on and so forth. Things are often discussed locally. Fine. Okay. So this is the basic case to talk about in this way, okay, and this is sort of a motivation of the implicit function theorem. The implicit function theorem actually deals with this, that when you are given a level curve, then whether that level curve, or rather the level curve locally admits some function whose graph is that part of the level curve. That is exactly what the implicit function theorem deals with, okay. Now this is sort of the things which we understood in the 2-dimensional and the 1-dimensional case, but rather we can also talk about in the general case. So suppose we have a function g from Rn to R, and so g is some function, and suppose we have some function g from Rn to R, then what will the graph look like? So the graph will look like x gx and the collection of all these points, right, such that x is in Rn. Now this is quite obviously understood that this x is in Rn, so it will admit n tuples, and the image of x under G, since G is real valued, so it will give rise to a 1 tuple. Therefore this is a subset of Rn plus 1, and this we have seen while we have studied the graph in the 1-dimensional case, that if you have a function from R to R, then the graph is inside R2, right. So this actually, so there we had a graph had a curve, and it was a 1-dimensional thing. The geometric structure itself was a 1-dimensional thing. So here we will have an n-dimensional surface in Rn plus 1. So this graph is just a just a n dimensional surface in Rn plus 1. Okay. This is something which we typically call a hypersurface. Okay, fine. Okay. Now the question which we can actually take up to n dimensional case, that whether we have a function from, suppose I have a function from Rn plus 1 to R, and I choose the points x in Rn plus 1 such that f of x is some constant c. So this is basically the level curve. So the question immediately arises is that whether, let me write it in the next page, whether locally there exists some function g from Rn to R such that this level curve x in Rn plus 1 such that f of x is equals to c, this is actually the graph xgx where x comes from Rn. Fine. So this is the question which is dealt in case of the implicit function theorem. Now suppose this level curve is given to you geometrically. Okay, if this level curve is given to you geometrically, it is given as some surface, then you can obviously try with the vertical line test, and you will be able to observe that if this level curve satisfies the vertical line test, then it is possible for there to exist a function whose graph is this level curve. But obviously you cannot talk about the geometrical structure of a 4-dimensional or a 5-dimensional surface given in paper, right. So the obvious structure you will be getting hold of will be an algebraic representation of these level curves, and whenever you are given an algebraic representation of these level curves, it is not possible in general to talk about the vertical line test, right. Therefore there must be some way to possibly analyze this situation given the level curves algebraically, fine, and that is where the implicit function theorems come in hand. So I am stating this theorem here, and in the next lecture we will be proving this theorem up. Okay. So this is the implicit function theorem. So what does this say? Let E in Rn be open, f be a function from E to R which is continuously differentiable. Let y be a function from y1 to yn, be a point in E such that f at y is 0 and the partial derivatives in terms of the nth coordinate of y is non-zero. Then there exists an open subset u in Rn minus 1 in 1-dimensional lesser surface containing the other n minus 1 coordinates of y containing y1 till yn minus 1, an open subset V of V of E which contains y and a function g from u to r such that g of y1 till yn minus 1 is just yn, so it is a real valued function, and the level curve of f v such that f of xn is 0 is exactly equal to the graph of g. okay, such that x1 till xn minus 1 is contained in U. Fine. So, what it typically means is that is the level curve at the origin, the level curve at 0, this admits, or rather is a graph of a function over, we have chosen a smaller set, over U. Moreover, we have an additional thing. Moreover, this function whose graph is this level curve, that function is differentiable. Moreover, G is differentiable at the first, or rather the n minus 1 coordinates of y, such that, and with the structure of it is given in this way, that the partial derivatives of G at this point is given as minus del f by del f del xj of y divided by del f by del xn of y, and this happens for all 1 less than equals to j less than equals to n minus 1. Fine. So, this is the complete statement of the implicit function theorem. The theorem looks to be very complicated and very confusing, but actually it is a very easy consequence of the inverse function theorem. So, I am just writing it up here. This can be thought of as an application of the inverse function theorem. In some books, I guess you will also see the inverse function theorem to be an application of the implicit function theorem, but rather we will follow this approach. Okay, fine. Yeah, so that's it. And if I just go through the statement once more, there it is very trivial statement. It exactly abides by whatever motivation we talked about, that if I have a function which is continuously differentiable, we will see why we require continuous differentiability. And you can in fact go through the examples which we talked about before stating this theorem, that continuous differentiability is actually required. So, what it basically says is that if I have a function from E to R which is continuously differentiable, I choose a point out from E where the function is evaluated to be 0 and the partial derivatives at that point are non-zero, then we will get an open subset in one dimensional lesser surface which contains the n minus 1 coordinates of y, such that G maps this n minus 1 coordinates to the nth coordinate, and the level curve at 0 is basically the graph of this function G. And then we have also given a structure of the derivative of G, and we have the fact that G is differentiable at that point at the n minus 1 coordinates of y. Fine. Okay. And in fact, the thing is that if we find that the partial derivative at y, partial derivative at the nth coordinate of y is 0, but the partial derivative at some jth coordinate of y is non-zero, then this complete implicit function theorem can be manipulated to talk about with the jth coordinate. In that case, we will take the subset u in Rn minus 1 to contain all the other coordinates rather than the jth coordinate, and everything in this part xn can be replaced by the jth coordinate, fine, or yn can be replaced by the jth coordinate, fine. Yeah. So, this in general can be talked about any particular coordinate of the vector which we are talking about, but rather this is a more simpler case to talk about, fine. Yeah. So, this is all about this lecture. In the next lecture we will prove the implicit function theorem, and so meet you guys in the next lecture.